So, now what we will do in this part of the lecture is I have two very senior project staff with me, Abhirami and Zuhaib, who are working with me for some time on a very pet project of ours, and that is related to energy monitoring. So, let me go back and write a block diagram for you. Joule Jotter, Joule, Joule Jotter is our case study. And what is this case study all about? We are trying to show you a complete run through of the code base developed for this energy monitoring hardware plus software developed in the lab. Developed in the Zen lab, okay. And as I mentioned to you, Miss Abhirami and Mr. Zuhaib Ahmed were involved in this project and are very passionate about this project. So, what does this hardware actually comprise of? This hardware, I will just point you to this piece of hardware that was developed. It is still in prototype stage. Look here, what you see here is a normal 220 volt plug extension box. Let us say there are many loads connected to this extension box and you are interested in measuring the VRMS, IRMS, power output, okay, power factor, all these related parameters of that plug point, okay. You are interested in different loads. So, loads, you want to completely characterize the power consumption of the load. Essentially you will end up with some time series data, how voltage varies over time, how current varies over time, how does power factor fluctuate over time, how does VRMS and IRMS look, and all of that. So, let us get to that slowly step by step. But before that, let me point you to different elements which is part of the product that was developed in the lab. So, what I can show you here is that this is the basic from 220, it is a step down transformer. It has two tappings. One tapping is to provide what is known as a PT input. So, if you take the transformers, the sensors which are required for measurement of these electrical parameters, you need what is known as a PT. PT stands for potential transformer, CT stands for current transformer, okay. So, this transformer that you see here has two tappings. One is it works like a sensor for energy monitoring, and it also works as a transformer for powering the electronics. The electronics is here, I will show you the PCB in a little bit detail. What you see here, this component here is the CT, which is the current transformer for measurement of all current related to, in order for you to get the current time series you need this. In order to get the voltage time series you need to put the PT, okay. And the full electronics system is here. Let me show you against this circuit, this PCB against the camera, and let us zoom in a little bit, okay. Let us try and zoom in a bit closer to see what are all the different elements which are there in this board, okay. You can see that this massive looking chip here, a little more closer please, okay. So, this big one, this big chip here is the microcontroller. This is MSP 430. So, let me write it down for you. Yeah, so the controller of interest is MSP 430 F 5438A. Look at the packaging information, QFP package, not QFN, it is QFP. This is QFP. quad flat package, right. That is the chip here. This system that you see here, this is indeed the radio module, which is called CC 3000. For some reason this radio module gave us some trouble. We will discuss that interface to this radio module separately. So just to complete the schematic capture as we go along, I will write MSP 430 like this, and I will connect the CC 3000 through a it is connected through a SPI bus, right. This is connected through an SPI bus, and this is the radio module. CT and PT are connected here. Okay, so this is the MSP. Okay. Then what else do we have on this board? Obviously it has to be powered, so you need a rectifier chip. So you can see this is the rectifier chip. Then input, AC input is fed through here after stepping down in an appropriate manner. There is an LDO here, the LDO is here. LDO's C in and C out capacitors are here. This is the C in capacitor, this is the C out capacitor. Let me hold it for you. This is the C in and this is the C out capacitors of the LDO, and what else. So these are the 2 channel inputs that this energy monitoring chip can do, which means the inputs obviously cannot go into MSP 430 because it is a controller. It uses a microcontroller system. So I am actually going to replace this with ADE 7953, which in turn is connected to the MSP 430, and MSP 430 in turn connected to CC 3000, and CC 3000 providing you the radio, and this is an SPI module. So you can see this is indeed the right schematic. Okay. As we develop the story, we realize that CTPT have to go to an energy monitoring chip from analog devices, and this chip is again there is a requirement for another I2C here. Now if you are asked to choose this microcontroller, you obviously have to choose something that can support at least one SPI and one I2C. So right, clearly MSP 430 is a good choice for this because it does support these things, this ability of having I2C as well as an SPI bus, and this controller itself, this energy monitoring chip itself will have an internal controller which can do several things for you. Obviously when you want to gather data over an I2C bus, this ADE 7953 will have a number of registers which you have to configure for the purposes of calibration. Therefore we should see that part of the code, how MSP 430, which is the controller of choice, is actually able to pass commands to ADE 7953 and configure some of the registers inside the energy monitoring chip. As I mentioned to you, our final working circuit for a long time, although used CC 3000, we then shifted out to support the radio communication over a very popular Wi-Fi module called ESP 8266. Okay. So this part was removed. In fact it will continue to be there, but we just do not use this. All the data, after all the acquisition is done, it is given to this module over a UART port. Now if you ask yourself this question, how will I choose a controller? It is insufficient to say I need one I2C and one SPI, but I also need 1 UART, right. Now you also need sufficient amount of programming pins if you are interested in using if you do energy monitoring and you want to do an actuation, you will definitely need a number of GPIO lines in order to control perhaps lighting loads or relays and so on. So a number of GPIO pins are also required. So you have to choose a controller which will support all these peripheral support as well as support for communication over very popular Wi-Fi modules, which is typically like the ESP8266. Now I struck this off because this is a very early module from TI. They have improved versions of this chip, although we did not want to change anything. This was one of the first IoT Wi-Fi module, and it as the chip was not very stable, we had to apply a number of patches in order to ensure that it would work satisfactorily. Very soon what would happen is it would hang. Okay, so communication between the gateway and this unit by itself was often a buggy situation. So we had to shift to another popular one, and indeed this is a very popular IoT Wi-Fi module, which we will try and see if we can spend some time understanding. In fact, Zuhaib has spent considerable time trying to tune this Wi-Fi module for communication. Essentially this Wi-Fi module supports both Wi-Fi direct which is peer to peer Wi-Fi, and it also supports a it supports like a Wi-Fi hotspot access point. Okay, so it is a very popular one which is available for about 200 rupees. You should be able to buy it, and it is a Chinese product, I think, from Shenzhen, very popular module, but available locally, so one could easily use it. So this is in brief the hardware. Let us shift quickly to some good aspects of this of the software architecture of this module, just to give you a feel of how one can develop hardware products in a IoT, how you can actually build IoT products for several applications. In this case, this is specific to the energy monitoring hardware. Alright, so you can see that you have to program this MSP 430, right. So you need a JTAG port for that, JTAG, and on JTAG we use this tool called IAR Workbench. It is a very powerful environment under which one can develop code for MSP 430. Different targets are available, and we have chosen MSP 430 as the target processor, and this is available. So we have used IAR Workbench for all the code development. That is one part. Then finally what you also need is an Android app, right, whereby users should be able to hold a phone, and get their data, not only get data but also configure this their home devices, right, because we mentioned that there are 2 CT channels and 2 loads can be connected, home loads. One could be a washing machine and the other one could be let us say let me take a example in the kitchen, that is much simpler. One could be a mixer grinder, and the other could be a refrigerator, fridge, I will call it simply fridge. Okay. Both these systems you want to monitor, and you actually want to configure and say this is the mixer's Joule Jotter and fridge system that I have, this is the complete system that I have, this system I will just circle it like this, and say this hardware is for mixer and for fridge you want to configure, right. So, all of that you should be able to do as a end user using a simple Android app, okay, and that Android app should be quite friendly enough, and those commands should be configurable through this Wi-Fi module. So, in other words, the Wi-Fi, the smartphone which also has a Wi-Fi is used to configure the devices which are connected. So, that is a nice that is another requirement in order to make your in order to build your IoT products. So, let us see how this the Android app works with the Joule Jotter, the Joule Jotter Android app. So, let us go there and click on it. You will see that ZenLabs Joule Jotter app opens. There are 3 possible configuration, 3 possible options here: configure, leave it at default, and collect data and perhaps see data, okay. So, visualize data. Let us go to configure data, and here you can see you can specify the Wi-Fi name that you want to connect to. Go down, you can choose the Wi-Fi name, right, and let us choose as ISC WLAN. You can set the password, you can set the sampling, set the password to something there, and then you can set how many samples you need in 1 minute. Let us say no, you need every 20 seconds. This is every 20 seconds you will get a sample of all the parameters that the chip can monitor. This is so that means you get 3, 20 seconds you get 1. So, in 1 minute you get 3 samples of IRMS, VRMS, power factor, then average that is peak power and other related parameters. Then you can give the name for the 2 devices that you want to connect. You have device 1 which can be refrigerator, TV, whatever you want to configure, and let us say microwave oven or a mixer. So, microwave oven and mixer are mixer grinder are typically those which are inside kitchen. So, you just type all that and then just press configure button. It configures and then connects to the system and essentially passes all these parameters on to the Joule Jotter piece of hardware. Okay. So, let us go back and look at how should we go about working with this Joule Jotter in order to get our IRMS, VRMS, output power, power factor, so on and so forth. The heart of the whole Joule Jotter indeed is this chip called ADE 7953. You can see it is a single phase multifunction metering IC and it has a number of features. You can see that it has one of the important things, it has less than 0.1% error in active and reactive energy measurement, provided you do adhere to the data sheet in its proper manner, in its proper way. You have to calibrate the resistors, you have to calibrate the equipment using standard equipment, you have to calibrate the Joule Jotter with standard equipment, only then it can give you assurances of 0.1% error. It also says that 0.2%, less than 0.2% error in instantaneous IRMS measurement is possible. Again, this always means that you have calibrated the IC properly. At the time when you boot the system, you have to ensure that you calibrate it correctly. It has a bandwidth of 1.23 kilohertz for all its operation, and you can use different type of sensors, including what is known as a Rogowski coil sensor for the measurement of current, okay, for accurate measurement of current. Of course, this would mean that an additional piece of hardware is required, but that is besides the point. Let us now go to a very important part, which is the register settings of this IC. I want to point you out in this data sheet to a register called IRQ Stata. Now look at what it says about IRQ Stata. Once the startup sequence is complete and the ADE 7953 is ready to receive communication from a controller, microcontroller, the reset flag is set in the IRQ Stata register, right. An external interrupt is triggered on the IRQ pin. The reset interrupt is enabled by default and cannot be disabled. Hence, an external interrupt always occurs at the end of power up procedure, hardware or software reset. Let me show you in the code the point where IRQ Stata is actually this particular register setting is actually enabled. So, let us go there to that part of the code. As you can see, this is IAR workbench IDE. Let us increase the size if required, so that you will be able to see them a lot more clearly. I think we should show that a little, yeah. So, there you are. So, you can see that IRQ Stata register, SPI register read 32 bits for ADE 7953 IRQ status, IRQ status from current channel A, right. There are two channels as we described, IRQ Stata A and IRQ Stata B may be the second one. So, this is how you would actually write, you would have to configure, do a register setting. Let me now also point you to other important registers going back to the data sheet. So, what are we trying to do here? You have to read the data sheet, go back and implement it in source code, that is the key point here. Let us go to IRMS A as a possible as one of the other register setting. Here the IRMS A register says that this is a 24 bit unsigned RMS measurement for current channel A and current channel B available in this two registers. So, if you are interested in reading IRMS from channel A, you have to use this register, the value is stored in this register. Now, let us go and see. So, what should happen? Both of these registers are updated at what rate? At 6.99 kilohertz per second kilohertz. At this rate they are updated with full scale channel inputs on current channel A and current channel B. The expected reading of IRMS A and IRMS B register is some value. Okay. Now, let us go back and see what exactly, how exactly this is done in source code. You can go back and see here that SPI read 32 bit for ADE, IRMS A read the current value IRMS from current channel A. So, you can see data current underscore current is equal to SPI register read underscore 32 ADE 7953 underscore IRMS A, right. So, if you do this, you are actually reading the IRMS A register. This is a 32 bit register and this 32 bit register is being read. Similarly, you can be talking about IRMS B and so on. Let us go and look at IRQ NA, ENA. Let us look at IRQ ENA. Let us look at IRQ ENA and let us see what actually this does. This is IRQ enable A, right. So, these interrupts are disabled by default and can be enabled by AEHFA and AEOFA bits in the IRQ NA register. This is each this register, multi-bit register has a name for each bit position. AEHFA and AEOFA are 2 bit positions in the IRQ NA register, right, and that address is mentioned there for current channel A and current channel B. Let us go back and look at these two IRQ NA and B in source code. You can see that SPI write underscore 32 ADE 7953 underscore IRQ NA, right, and IRQ NAB. So, the big summary here is that you will have to look at the data sheet and accordingly write your code in an appropriate manner and debug your code Let me point you to the top extreme left here, which says that this debugger that we are using, the environment software environment tool, indeed is the IAR embedded workbench IDE for MSP 430. Your problem does not end here. Actually you have to do, in order to get accurate values and try to meet the data sheet requirements, you also have to do calibration of some of the registers. That again is another document. So, now let us go and open up that document and read the starting part of that document. It says calibrating a single phase energy meter based on ADE 7953. What it simply says is, application note describes how to calibrate ADE 7953. It details the calibration procedure, including equations and examples on how to calculate each constant. ADE 7953 is a high accuracy single phase metering IC that allows both phase current and neutral current to be measured simultaneously. It provides a variety of energy measurements, including active, reactive and apparent energy, along with current and voltage RMS readings. A variety of power quality features, including no load, reverse power and a direct power factor measurement, are also provided, right. Let us see what are the calibrations that you have to do. Down below, if you go and browse through this document, gain calibration, phase calibration and offset calibration are the most important things here. So, gain calibration, as it says, it is always required. Phase calibration, when we are using CT, in which case we are, it is often required, and when using a shunt it is not always required. Offset calibration, perhaps when looking for high accuracy over a large dynamic range, it is often required. It is not usually required for all other meter designs. So, in a way offset calibration may not be so critical when you are measuring pluggable loads in homes, but gain and phase calibration definitely you have to do. Let us now go back and look at the source code and look at these calibration registers which are done in the source code. Let us look at gain calibration to begin with. So, you can see that gain calibration is you can see here I calibration, V calibration are all part of the I calibration has a number there which you have to prime into the register. V calibration also has a number, and these two numbers are actually available from that other data sheet that we went to, and these are configured here. So, gain calibration, phase calibration are important and they have to be done. Let me introduce you to this very exciting chip. This is called ESP8266EX, and this is the Wi-Fi module that we have used in our Joule Jotter hardware after we bypass the existing CC3000 Wi-Fi module, right, because it was buggy and so many other issues were there. This ESP8266 actually has a complete TCP/IP stack, embedded stack running on it, and it's some of the good features of this chip are that it supports the standard Wi-Fi protocol 802.11, many versions BGN, EI and all that. It does Wi-Fi direct, peer to peer support, it does peer to peer discovery. You could have it as a group owner or as a group client in this peer to peer mode. It can work as in the infrastructure mode, it can be configured as an access point, and it has security, beautiful security features, CCMP, CBC MAC, TKIP, CRC, all of that, which means it is indeed a chip which is an embedded chip, embedded module, but very powerful, has all the security features embedded in it, and it is as I mentioned already has a TCP/IP stack running on it. It is just not working for not just working as either peer to peer Wi-Fi direct access point, but it can also be used for range extension purposes, which essentially is for a repeater functionality. So many nice features are possible on this using this module. Okay. So however, look at the okay, before we go on to that, let us look at the RX sensitivity, receiver sensitivity. It is down to -91 dBm. If it is B, it is if it is G, it is -75 dBm, and N is -72 dBm. So and it works in this nice voltage range. Operating voltage range is 2.5 to 3.6. Alright, so essentially as I mentioned, it is it has support for embedded TCP/IP stack. Mainly it supports IPv4. Okay, so that is perhaps one limitation of this system, and newer modules with IPv6 stack are also expected to come. Nice applications possible: home, smart plugs, lights, mesh network, baby monitors, IP cameras, sensor networks, and so on. Really a good Wi-Fi IoT module for several applications. Many YouTube videos are available for this very exciting ESP8266 Wi-Fi module. However, if you put it into the framework of what we did in the Joule Jotter prototype hardware, we now ended up with another type of IDE framework, which essentially I want to draw your attention to this screen, which is which essentially talks about the Arduino IDE, right. So it is, so now you can see all the ADE configurations that we did earlier used IDE used IAR workbench for configuration, and only for the purpose of configuring the Wi-Fi chip we had to shift to the Arduino IDE. Now there is something interesting that we have configured this chip and trying to use its power. If you cold start the Joule Jotter, I mentioned to you that we need a Android app for configuring several parameters, right, and that essentially means you are in the soft AP mode. The ESP module is put into soft AP mode, and users can type in the parameters of interest like device names, sampling rate, and all that. You can use it, you can use this ESP in the hotspot soft AP mode. Soon after the configuration is completed, the module, Joule Jotter module, can connect to your home gateway. Okay, can you connect to your home gateway access point. In other words, you can shift between very seamlessly, you can shift between the soft AP mode and client. I just want to show you that piece of code which will allow us to which we have written, developed in the lab, which will allow you to move between the two. Let us first expand the screen such that there is some legibility in terms of the mode that we want to show, that is between soft AP and as a client. If you look at that setting which has been marked in highlighted part, the Wi-Fi dot soft AP, I am not able to show you clearly if it can be expanded, configuring as access point. You can see that it is actually being configured as a soft Wi-Fi soft AP, and so this is the mode in which users can fill in all their parameters from an end user's perspective. Then it can also be configured for the client purpose, and that part indeed is perhaps another method which the lab development takes place, and this is the method to connect to a Wi-Fi access point. As you can see right here, it is called void Wi-Fi, and then this particular thing indeed connects to the SSID perhaps announced in your homes. So, very powerful, interesting chip, IoT chip, Wi-Fi chip for several applications.